And now we come to the normal distribution. We're going to make the jump from discrete distributions to continuous distributions, and we have to talk about the concept of density curves, and we're going to focus mainly on this one called the normal distribution, which has the normal density curve. A lot of books put this up in the front in the descriptive statistics because technically it is. We're going to talk about a way of using this continuous function to describe a distribution that happens to have what's called a normal distribution. I always cover it a little bit later in the class when we're getting ready to do inferential statistics because it really, to me, is a nice transition from the discrete things we've been doing to inferential statistics, which is going to rely heavily on the normal distribution and similar concepts. So the first thing I'm going to do is talk about how we can get a graph where the area under the graph in certain regions tells you the number of the distribution that fall in there. Okay? So in our very first section, we looked at graphs and how to make different types of graphs. And for quantitative data, we can make histograms. And what we did was we divided our data into intervals, and then the height of the histogram represented the number of the data points that fell within that particular interval. Like I have labeled here, here's an example with two of them. The green one is a normal histogram where the height are the counts. Okay, so it says the height is 7 at the bar I'm pointing at. This one has a height of 7 between 40 and 50 here, because 7 of the data points are between 40 and 50, including 40 but not 50. And when you use software, you have to decide whether you want to include the left or the right endpoint, and different software will do that different ways. You can make GeoGebra do it either way, but it includes the left endpoint by default, unless you tell it to include the right. But anyway, the point is the height of that bar tells me the number of data points that fall within that range from 40 to 50. It would be easy enough to divide and convert to percent. Okay, the particular data I'm working with here, there were 19 numbers. 7 of them fell between 40 and 50, and that works out to be 37%, 0.37. So instead of plotting a height of 7, I could plot a height of 0.37, so that the height this time, instead of telling me the number that falls in the region, it tells me the percent that falls in the region. Okay? So that's not too big of a leap. But the final leap we're going to do here, I'm zooming in a little bit on the picture. I'm zooming in on the blue one and then going to make this new one the red one, which is a really short graph. Everything's less than 0.1 if you look at it. But what I've done to get to the red graph is divided each bar's height, which was the percentage, by the width of the bar. And so what I have accomplished by doing that is now the area of the bar is 0.37. which tells me that 37% of the data fall in that region between 40 and 50. Okay? So the point is it's possible to first convert to percent, and then when you do a histogram, to divide each of the bars by the width of the histogram, and the purpose of that would be to get a density histogram, where instead of the height of the bar, but the area of the bar tells us the percent, or proportion as a decimal, of the population or of our data that falls within the width of the bar there in this case. Okay? So that's what a density histogram is. The area of the bar would tell you the percent of the population that falls in that interval. Okay? The reason we do that is because calculus actually gives us ways to compute areas under curves. And for statistics purposes, we can use calculators and tables and things to get the numbers without doing calculus. But mathematically, we have ways to compute areas under curves. So density curves in general. So in the particular book that I'm using right now, it's chapters 1 and 2, where we talked about graphical displays and numerical ways, such as histograms and box plots and different ways, pie graphs, pie charts, things like that if you had categorical data. But those give us tools for describing distributions. Density curves add a way that we can do that sometimes when we have continuous variables that are very nicely behaved. Okay? So when you're exploring quantitative data, always look at your data, make whatever graph is most appropriate, or make several graphs. Look at the overall pattern. If there is a nice overall pattern, you can describe the shape, the center of the spread. Is it skewed left, skewed right, symmetric, those types of things we talked about. Look for outliers. Are there striking departures? Okay. Calculate the numerical summaries. You can find the mean and the standard deviation, or the 5-number summary. And then what we're adding here is sometimes the overall pattern of a large number of observations is so regular we can describe it with a smooth curve. And we're going to look at smooth curves called the normal distribution. Okay? So here's an example. This is a normal distribution. You might be familiar with this shape, whether you've heard the term normal distribution or not. Sometimes we call it a bell curve. Okay, so here's a histogram, as it says here, a histogram of vocabulary scores of 947 seventh graders on some sort of standardized test of however it's measured here. Apparently the scores range from 0 to 12 maybe. Okay. But the point is we have some data that when we plot it, we get a histogram that is pretty nicely shaped. It's roughly symmetric. And if we go across, it's not perfect. You know, when you go from real world data to theoretical models, we have to smooth them out a little bit, right? But it's not perfect, but it's close. It's approximately normal is what we would say, meaning it's symmetric and bell-shaped with the peak in the middle like this. We'll talk about the specific shape of normal curves. We describe them as bell-shaped because they kind of look like a bell, but there's something very specific about the mean and the standard deviation, I'll say in a few minutes. So that's the idea of the data. It may not be perfect, but if it's close enough, we can draw a nice smooth curve or a graph through it, which is called our mathematical model. And this particular one is a normal distribution. Okay? And so the idea is if you're looking at the histogram, you could add up the area of all the bars to figure out the proportion. And if you convert to a percent, the percent that falls in a certain range. So for example, if we shade all of the bars here that are less than or equal to a 6.0, that would tell us if we added all those up, the areas of all those, if we added them up, it's 0.303, which tells us that about 30% of the students in this sample scored a 6 or below. That's not exactly what you get if you use the curve to approximate it instead, but it's really close. You get 0.293, okay? So 29% versus 30%. So if I were to use the actual curve to approximate the area, you can see there's some places we're going to underestimate, some places we're going to overestimate. But we get a pretty accurate answer in this case. You know, it's pretty close, 29% versus 30%. So it's not perfect when you use the nice smooth curves, but they give us nice tools that we can use. Just like when we use a straight line to approximate a scatter plot. So density curves, to summarize, you can have other types of density curves. One that a lot of books talk about is a uniform density curve, which is just a rectangle. It's a horizontal line if you plot it, and then the area of the rectangle would be 1. It would have to be by definition of a density curve. The way we divide out to create the density curve, it's always going to be I would call it a positive graph. Thinking about algebra, it's always on or above the horizontal axis, the x-axis, if you want to think of it that way. And the area under it is exactly 1. It has to be because it's representing 100% of your population or of your data. I'm talking in terms of population because we're starting, say, to make this shift toward inferential statistics where we're going to take samples and think about larger populations. So a density curve describes the overall pattern of the distribution. The area under the curve and above any range of values on the horizontal axis will tell you the proportion of the observations that fall in that range, such as on the previous one. We had, if you did the area from 0 to 6, the area between the curve and the axis from 0 to 6, if we use the curve, was 0.29, because approximately 29% of the population was between 0 and 6 on their scores. Okay, so that's what a density curve is.